I think we can start.
Sure.
So, dear participants, very good afternoon to all of you. So, today for this session, we have a very renowned expert of antenna field, Professor Amrendu Patnaik, with us. So first of all, I thank Professor Amrendu Patnaik for accepting our invitation for delivering the session. Professor Amrendu Patnaik received his PhD degree in electronics from Behrampur University, Behrampur in 2003. Then from 2004 to 2005, he was with the University of New Mexico, USA as a visiting scientist. He is currently a professor of New Mexico. He is currently a professor in the Department of ECE at IIT Roorkee. He has authored and co-authored over 100 peer-reviewed papers in international journals and conferences, and co-authored one book on compact antennas for high data rate communication, ultra-wideband and MIMO technology, which is published by Springer. And Sir has also published one book chapter on neural networks for antennas in Modern Antenna Handbook, which is published by Wiley. Current research interests of Professor Patnaik include plasmonic antennas, antenna array signal processing, application of soft computing techniques in electromagnetics, CAD for patch antennas, EMI and EMC issues. Sir is a recipient of the IET's Sir J.C. Bose Award in 2000, the URSI Young Scientist Award in 2005, and the Voice Class Fellowship from the Department of Science and Technology, Government of India from 2004 to 2005. Sir was the chairperson of IEEE Roorkee subsection from 2015 to 2017. And he was an IEEE APS Region 10 distinguished speaker during 2015 to 2016. Sir is serving as at the editorial board member of the International Journal of RF and Microwave Computer Aided Engineering, published by Wiley, in addition to the advisor to many conference, the organizing committees and other journals. So with this brief introduction, I invite Sir to take over the session and share his expertise with the participants. Welcome, Sir, to the FDP. It's over to you, Sir.
Thank you. Thank you very much for that nice introduction. The topic for today's discussion is graphene flexible antennas. Although at the outset, I must confess that I am not an expert in this particular field, but recently we have started working on this area. Okay. So I will share some of my experience as far as graphene flexible antennas are there. This particular material, when it was discovered in 2010, it was named as miracle material. And the scientists during that time, they said it's a miracle material that could revolutionize the world. Although in today you will find a number of applications of this particular material, particularly in sensor technology. But in today's discussion, we are going to discuss what is its role as far as antenna technology is there. So what exactly is this particular material, graphene is? It's a one atom thick layer of carbon arranged in a honeycomb lattice form, right? So when millions of these are stacked on one on top of the another, they form graphite. So basically, graphene is a single layer graphite, right? So what is graphite? It's a mineral consisting of carbon which is found in pencils. So this material These are the scientists who discovered this particular material in 2010. They got the Nobel Prize for discovery of graphene. So Professor Novoselov, who is the student of Professor Andrew, they both in University of Manchester they discovered this particular material. So why this graphene material for antennas, in particularly for wearable applications? The main reason is it's a very flexible material. You can see in these pictures, the material is very much flexible and transparent also. It's almost 97% transparent. These are the two main reasons why this material is preferred for wearable sensing applications. So you can see in these pictures that these antennas can be printed or transistors can be printed on this graphene using this graphene layer. These antennas and transistors can be implemented into dimension. So as I told you, because it is very thin, very flexible and transparent, because of those reasons, these are nowadays this is the very favored material for wearable applications. You can find number of applications of this material as far as wearable sensors are there, although other applications are there of this graphene material. Okay, but as far as our research is concerned, specifically we are using this material for antenna designing, not specifically for wearable applications, but the same thing that we are developing can be used for those type of applications. But as far as today's discussion is concerned, I am going to outline few major properties of this graphene material, which are suitable for antenna applications. Okay, so we will discuss those specific properties and exploitation of those properties to make efficient antennas, right? So we'll start with that introduction. Then we'll see the antenna designing using these graphene materials and how to improve its performance of this graphene material antenna that we will see. Then because those who are working in antennas, they must be knowing that the most widely used material is metal, that too particularly copper, right? So what is the role of this graphene material when we are combining that with that metal? We'll see how it is playing a role as far as metallic antennas are there. Okay, then we will conclude. The first major property of this graphene material is that the antennas made up of this material is working effectively in terahertz frequency range. 10 to power 12 hertz is 1 terahertz. So it is these graphene antennas are working effectively in this particular frequency range, terahertz frequency range. Okay. So at present, the focus is in the low terahertz frequency range, 0.1 terahertz to 10 terahertz. Why? Because of the availability of source, terahertz source in this frequency region. So in addition to the flexibility nature and the transparent nature of the graphene material, another important property because of which it is suitable for wearable applications is this terahertz frequency or terahertz radiation is non-ionizing in nature. It's non-ionizing in nature. And because of this, unlike X-rays, it will not harm much to human tissues, right? That is another big reason why this material can be used for wearable applications. In addition to that, the other properties of these terahertz frequencies is that high penetration with low attenuation, high resolution imaging capability because the frequency is very high, so the wavelength is very less. That is the reason why these are the preferred frequency range for imaging applications. Okay. You will get very clear images in this particular frequency range. Then some other properties of this particular frequency range is spectroscopic capability and low scattering and high intensity. So if you study the literature, today you will find the application of this particular frequency range, terahertz frequency range, in many areas, including communication. You will find its applications in military and defense, biomedical applications, spectroscopy, sensing applications, imaging applications. As I told you, you are going to get very contrast images if you use this particular frequency range. You can find applications in security, and most widely these people working in astronomy and atmospheric research, they prefer this particular frequency range. So what are the when you are trying to use this frequency range for wireless communication? So what are the properties that are preferred? It's more directional, this terahertz waves. Because of high frequency, in this frequency range, you will get large bandwidths. And because of that large bandwidth, you can get high data rate, very high data rate of the order of 100 plus gigabits per second. So from communication system point of view, wireless communication system point of view, this particular frequency range is, if terahertz can be used, then you are going to get a very high data rate. But at the same time, what is the disadvantage of this frequency? Is high path losses. So as the terahertz wave is propagating through a medium, it suffers major losses. So when you are thinking of using this frequency for antenna applications, you need to make very directional antennas. Why? Because in this frequency, path loss is very high. So you need to make very directional terahertz antennas, right? meaning the antennas that you are going to design in this frequency range should have high directivity. In terms of antenna terminology, you can call it as highly directive terahertz antennas has to be designed. So because antenna is a major component of any wireless communication system, so if the communication engineers are thinking of using this frequency for high data rate communication, so antenna engineers have to think of for designing high directive terahertz antennas. So nowadays you can find a number of publications related to these terahertz antennas. These are few of those typical publications you can find in the literature. The Journal of Infrared and Millimeter Wave Terahertz Waves, IEEE Transactions on Nanotechnology, then Applied Physics, Journal of Applied Physics, Transactions on Terahertz Science and Technology. So in these specifically in these journals, you can find terahertz antenna papers. So if you review those literature, you will find these three materials used for designing these terahertz antennas. Copper, the most widely used metal for designing antennas. You can find graphene terahertz antennas, and few papers are there where they have used carbon nanotube terahertz antennas. Okay. So when we started working on this, we thought of finding out suitable material for this terahertz antenna design. And because in the literature we found these three materials that have already been used for making terahertz antennas. So we conducted a study to find out which out of these three, which one is the suitable material for terahertz antennas. And we found that out of these three, graphene gives a better performance compared to the other two materials. Okay. Let me briefly go through that particular study. Okay, first let us see the graphene properties. So the left hand side, you see a graphite. It's a multi-layer, a number of layers of graphene will make graphite, as I told you in the very first slide. So a single layer of that is a graphene sheet. Graphene is the single layer of graphite. 3 million sheets of graphene would be 1 millimeter thick. So from this, you can find out the thickness of this particular graphene material. Okay. The interplanar spacing of two graphene plane in this graphite layer is 0.335 nanometer. Okay. It's a single layer of sp2 bonded carbon atoms. You can say this one, arranged in a hexagonal or honeycomb lattice form. You can see this particular diagram where the carbon atoms are arranged in a honeycomb lattice form, right? And with a carbon-carbon distance of 0.142 nanometer, the distance between two consecutive carbon atoms is 0.142 nanometer. And if you see the band structure of graphene, we are saying that electronic band structure of graphene, it's a zero band gap material. Okay. As far as the material properties of graphene is concerned, its mobility is very high, and the other properties which are suitable for antenna applications is the current density and the transparency. It's almost 98% transparent. Its tensile strength is also very high. Breaking strength is very high. That means these you can't break easily these materials. Okay. So because of these properties, you can use this material for designing antennas or wearable sensors. Now, if you see the specific properties of graphene at Terahertz, its conductivity can be tunable by chemical doping or bias voltage or magnetic field. This is another important property of this graphene material. What is that one? That the conductivity of this material can be changed if you apply a bias voltage across this material. Its conductivity can be changed, meaning because the conductivity is changing, so this property can be used for making reconfigurable antennas. So the conductivity changing means the antenna properties will change. If you change that bias voltage by applying just a bias voltage across this material, you can change the conductivity of this material. So if you are designing an antenna, the antenna properties will also change. Furthermore, it supports surface plasmon polariton in terahertz frequency range. We'll see what exactly this particular phenomenon is. So the conductivity of graphene, sigma, is basically the contribution is coming from two different techniques or two different methods. One is coming from intraband transitions, and another contribution is coming from interband transitions. So the contribution that is coming from intraband torque is this one, whereas the interband torque is this one, right hand side. Okay. So combining both these contributions, intraband contribution as well as the interband contribution, you can get the total conductivity of graphene. But it has been found that at low terahertz frequency, this intraband conductivity dominates over the interband conductivity. If you go towards higher and higher frequencies, then you will get this interband, you will find that interband conductivity or the contribution coming from interband transitions is dominating. But because at present the low terahertz frequency sources are available, so our focus is on this particular lower terahertz frequency. So in order to find out the conductivity of this material, we will use only this first term, right? So sigma S is sigma intra plus sigma inter. So you can find the detailed mathematical analysis in this particular publication. Now, one thing you can mark from this particular term is that it is dependent on EF, that Fermi level. Okay. So this is the first term at low terahertz frequency, right? And in the graphical plot, you can see how this conductivity is varying with the frequency. Okay, particularly in low frequency, low terahertz frequency range, how the conductivity is changing. Okay. So it's because the conductivity is changing. So the if you see the surface resistance or it is a highly inductive nature at low terahertz frequencies, and in particular at 1.5 terahertz frequency, you will find that the surface impedance is of this order, 42.401 ohms. So at low terahertz frequency, the material is highly inductive in nature. Okay. Now let's see what exactly that surface Plasmon polarity concept is. These metallic and dielectric interfaces can sustain surface Plasmon polariton waves at nanoscale region. Okay. So you can, from the figure, you can mark it's a metal layer, it's a dielectric layer. So in the interface between metal and dielectric, if light of certain wavelength is falling on this one, then it will create the atoms present on the surface or the interface between dielectric and metal. They create a vibration, and that particular because these bunch of these atoms are called surface plasmons, and because of that vibration, the frequency that we are getting is what is known as the surface Plasmon polariton concept. Okay. So photon or light of suitable wavelength with surface plasmons, this bunch of metal nanoparticles, they form the surface Plasmon polariton. Okay. So what is the nature of this surface Plasmon polaritons? It's sub-wavelength localization of electromagnetic energy. It's a localized EM wave, enhancement of near field intensity, and long range propagation. Okay, the wave that or the frequency that is created because of this particular concept, it can propagate to a large distance. And briefly, this is what is known as surface Plasmon polariton concept. And the resonance that is taking place in graphene materials is because of this SPP concept. Okay. So, what are the other plasmonic materials that are available? If you see the metal plasmonic materials like gold and silver, etc., they also support these plasmonic waves, surface plasmons. But they support those SPPs at optical frequency, not at terahertz frequency. Although these materials, these particular specific materials, they support surface plasmons, but they support it at optical frequency, right? suffers heavy losses. Furthermore, unlike in graphene, you can't get the tunable conductivity property in these materials. Tunability is not possible in fixed structures. Okay. Whereas in graphene, graphene plasmonic material, it supports SPPs, surface plasmon polarity waves at terahertz frequency, and highly tunable. As I told you, by applying a bias across these materials, you can change the conductivity. So when we studied the literature, in addition to graphene, we found the other materials that have already been used for making terahertz antennas. We found some papers have used carbon nanotubes also for making terahertz antennas. What's a carbon nanotube? It's a like if you make a cylindrical form of this graphene seeds, you will get carbon nanotubes. Okay. So because this carbon nanotube is made up of those graphene, that's why if you compare the properties, it is giving almost the same properties as that of graphene material. So if you study the literature of terahertz antennas, you will find some papers on carbon nanotube based terahertz antennas. Other material that have been used for making terahertz antennas is copper, because this is the most widely used material we are using in low frequency ranges, RF and microelectronics. So people have tried this material also to make terahertz antennas, but the biggest demerit is as the frequency is very high, so lambda becomes very less. So as you know, the size of the antenna should be of the order of lambda for the antenna to work effectively. So it becomes very difficult to make these thin copper lines that can be used as antennas. That means the fabrication process becomes very difficult. Okay. So it's a comparison of those electronic properties of graphene, carbon nanotube, and copper. So if you compare, as far as the carrier mobility and current density, on which the antenna properties are dependent, you will find the graphene is having the best properties in comparison to the other two. Although current density is same in both the cases C and T graphene because they are of the same material. So what we did, to find out a suitable material for making this type of flexible antennas, we designed 3 different antennas. These are all simulated results of same size. The lengthwise they are of same size. One is made up of graphene, another carbon nanotube, third one is using copper. Okay. We made dipoles of same size. And all these dipoles are sitting on a silicon dioxide substrate. Right? And you can mark the cross-sectional view of this terahertz dipole antenna. The length was, these are the specifications of these dipoles, 71 micrometer this and this. And we found This results for these three different antennas. The first one is for graphene dipole antenna. Although all are of same size, physical size is same. It is working well below 1 terahertz frequency, the graphene dipole antenna. Second one, carbon nanotube, it's resonating roughly around 1.4 terahertz frequency, whereas the copper one is working nearly equal to 1.8 terahertz frequency. Although all are giving the same type of radiation pattern, so we found that graphene is able to resonate at a very less resonant frequency. Or you can get, you can say that the compactness of these graphene antennas at terahertz frequency is much less. You can get a very high compact graphene antenna compared to CMP and copper. So once we found that graphene is giving better performance, then we tried to find out its resonant frequency. So this is the resonant frequency formula that you can find in some of our publications. And using that closed form formula also, we found that FR, the resonant frequency, is 0.81 terahertz, which is almost mixing with this simulated one. Okay, so in that way, we cross-verified the suitableness of this design or this framed formula for resonant frequency. So then we compared the radiation characteristics of all the three antennas made up of graphene CNT and copper dipole. You can find that, as I told you, it is resonating at a very less frequency compared to other one. Not only that, the reflection coefficient is much better than the other two, and you are getting a directivity which is much higher than the directivity of other two antennas.
Thank you.
If the size remains the same, physical size remains the same, you are getting better performance in case of graphene antennas, right? So in the next step, what we did is we designed all these antennas for 1 terahertz frequency. Okay, we designed all these antennas for 1 terahertz frequency. So by simulation, in trial error method, we fixed the size of these antennas so that all the three antennas will resonate at 1 terahertz frequency. And we found that the physical size of graphene antenna is less compared to the other two. And you can see the results for these antennas. So this first one for graphene, it's 68 micrometer length, is 99 micrometer length, and this is copper one, 139 micrometer length. And directivity wise also, it's giving better performance. So from these two studies, we found that out of all the materials that people are preferring for making terahertz antennas or flexible antennas, graphene gives better performance. Graphene antennas are that's why preferred for making these terahertz antennas. Okay. So you can find the details of this particular study in these two publications. Okay. One is material selection for terahertz antennas. Second one is performance of graphene plasmonic antenna in comparison with their counterparts for low terahertz applications. Okay. Then once we found that it is graphene is giving better performance, then we try to enhance the performance of this particular antenna. Okay. So what we did, again we studied that conductivity equation, and we found that sigma is a function of EF. You can find the presence of EF at different positions of in that equation. So that Fermi level in the first diagram, if you see, is at the Dirac point, but as I told you, you can change the position of this Fermi level of this graphene material by applying a bias across this material. Okay, so you can shift the EF level in the valence band, or you can shift the EF level to the conduction band, or in other words, depending on the presence of this EF level, you can use this material either as a conductor or as a dielectric also. Okay, so it can either be used as an insulator or as a conductor. So then, because it is dependent on EF, then we thought of using this material for making reconfigurable antennas. What exactly a reconfigurable antenna is? Those who are working in reconfigurable antennas, you can find either frequency reconfigurable antenna or polarization reconfigurable antenna or pattern reconfigurable antennas. So if a single antenna is capable of working at multiple frequencies, you can say it's a frequency reconfigurable antenna. Similarly, if a single antenna is capable of producing multiple beams, multiple number of beams at different times, then you can term it as a pattern reconfigurable antenna. Similarly, polarization reconfigurable antenna. So we thought of using this particular property of the changing or tunable conductivity property of graphene for making reconfigurable antennas. So you can mark the complex conductivity in this particular plot. You can mark the complex conductivity versus frequency. Okay. So with the different values of EF, Fermi level, right? You can find that the conductivity is changing. Okay, so if you are using this material for making an antenna, it's the antenna properties will also change, right? So we made a simple graphene antenna structure. What is that one? It's a silicon layer. Above that, silicon dioxide layer. And the graphene layer is sitting on that silicon dioxide layer.
No.
Okay.
बस मेरे को ठीक से रेंज का
And you can mark the cross section in this particular figure. So when you apply a voltage across this graphene layer, you can see that see this particular expression EF is dependent on VG. So when you change VG, that EF layer will change. So in turn, it will affect that conductivity of for that material. So when the conductivity of it will affect the antenna properties. So these are the properties of or the different dimensions of that graphene antenna. Okay. And it has been found that the thickness of this silicon dioxide layer, TOX, it plays a major role as far as the antenna performance is there.
आपको पता मैं क्या लगा रही हूँ 3 टाइम
So let us see
नारियल का
the
तेल लगा रही
behavior
हूँ
of
उसके
this
बाद भी मुंह
particular
सूखा
antenna.
सूखा हो जाता है
So when
नहीं
we
आती मैम
changed
मतलब
that
चलो जितने हैं वो तो मेरे है ही हैं
EF
काफी लेकिन मैं रोज
with the
नारियल का
help
तेल
of
लगा रही
a
हूँ 10 दिन हो
applied
गए
bias,
ड्राइनेस इतनी है
we found
नहीं पता हम क्या कर रहे
that
हैं मैम वो ऐसे तो 2 किट बनती है ना एक उनकी तरफ से एक
for
हमारी तरफ से
changing this
तो
EF,
उन्होंने बोला है कि आप देख लो
you
तो मैंने
need
कहा एक ही किट
this
बना देते
value
हैं
of
चाहे 8,000 की
VG,
बन जाए 10 की बन जाए
and
और फिर
because
उसको
of
50-50 कर
which,
देंगे
see, you can
तो मैं
mark
खुद
in
उनके
this
घर में
plot
तो कोई है
also
नहीं ना
with gate
मेरे को नहीं पता
voltage,
उनके
the
घर में तो है
VG
2 लड़के
voltage, the Fermi energy
हाँ
is also changing. Fermi energy is also changing.
ठीक है
This is the electric field intensity
हाँ जी
distribution at two typical frequencies. So what exactly it is showing? The current distribution on the antenna surface is changing. And as you know,
फाउंडेशन
all the antenna properties are
एक वो
dependent
फिट में
on the
बड़ा
current
सुना मैंने
distribution on the antenna. So because you can find that at two different frequencies that you have created with the help of two different EFs,
तो उसमें शेड भी
you
देखना पड़ेगा
are getting different current distributions,
ठीक है
right? So because of this, you are going to have different properties of the antenna. Let's see what are those particular properties. So we found that the antenna is able to resonate at different frequencies with the help of this EF. So basically, it was working from a 2 terahertz frequency up to 5 terahertz frequency. Okay. Or in other words, you can say that it can be used as a frequency reconfigurable antenna. Okay. But what is the difference between a graphene based frequency reconfigurable antenna and a metal reconfigurable antenna? Those who have those who are working in antenna field, you must know that for a frequency reconfigurable antenna or an antenna having the capability of working at different frequencies, for each frequency, each resonant frequency, your input impedance is also changing, right? So while designing metal frequency reconfigurable antennas, you need to take care of that input impedance. It should not change by a large value. So if it is changing by a large value, you can't get proper functioning of this frequency metal frequency reconfigurable antenna. But
अच्छा
in this case, in graphene reconfigurable antennas,
7 sec
we found that the input
हाँ जी
impedance remains constant.
वहाँ और भी
It is
सवाल है
not changing. The input impedance at all these reconfigurable
12,000
frequencies,
1200
at all these
तक
reconfigurable
लगेंगे ना
frequencies, it remains constant. Okay?
ओके
Antennas. The difference between metal
हाँ जी
frequency reconfigurable antenna and graphene based frequency reconfigurable antenna.
ज़ारा से जाके ज़ारा कहाँ
Is
है
by
डांटे
changing different the mobility of graphene material,
हाँ
we
जी हाँ
found that
जी
it is not affecting much as far as the resonant frequency is concerned.
ओके
Then we tested its radiation pattern. We found that at all these reconfigurable frequencies, it is showing similar radiation pattern.
ना वैसे बहुत रेयर लगेगी आई शेडो तो मैम
Then we found that in all these reconfigurable frequencies, it is giving a suitable or a proper directivity also, and with frequency it is also changing.
ठीक है
This is the comparison of the directivity at different frequencies, and we found that at higher frequency it is showing higher directivity. Okay.
अच्छा
Then we extended that single layer graphene antenna to
हाँ जी
bilayer graphene antenna. Okay. And you can find that see this one. The bilayer graphene consists of two coupled single layer of carbon atoms.
मैंने सोची
Each
है
single
5
layer arranged with a honeycomb crystal structure. Okay. So the previous thing that we considered was single layer graphene.
मैम
Then
सैटरडे
we
को चलें
extended
क्या फिर
that
अगर
to
आप बोले
bilayer
तो
graphene. Okay.
मुझे
So if you study its behavior,
आप मेरे को बता देना क्योंकि अब मैंने
the
एक चीज
forming
तो
energy of
लेनी ही लेनी है
both
मतलब ये
upper
मेकअप वाला
as
तो
well as
रेडी
this
करेगा
lower graphene layer can be dynamically controlled over a wide range by applying external voltage between the two graphene layers. So this was
तो फिर आप मुझे बताना
bilayer
इस फ्राइडे या सैटरडे एक
graphene
काम
antenna
खत्म करते
structure,
हैं
Terahertz antenna structure, right?
ठीक है
You can mark from these
हाँ
reflection
जी हाँ जी
coefficient plots that in the previous case we
अच्छा
were getting the reconfigurability around a particular frequency, but in this
हाँ
case,
एक वो भी तो
because
लेना
of the
पड़ेगा क्या
presence
बोलते
of
हैं ये
two
इसमें
layers
डोर
of
जो लगाते
graphene,
हैं
you can
कब है
mark that in the
ठीक है
contribution of one graphene
रोज
layer
लगाना पड़ेगा मोना मैम
is this bunch of frequencies, this bunch of reconfigurable frequencies,
हाँ
whereas the contribution from the other graphene layer is another bunch of
हाँ
reconfigurable
वो लिक्विड
frequencies.
आता है या लिपस्टिक टाइप में
Okay.
मैं मैम मैंने रहना तो
So
यहीं पर है यहीं से कॉलेज
the
धक्के खाने
concept
आ
of
जाना है ज्यादा तैयार नहीं हुआ
frequency
करूंगी
reconfigurability that you are getting in metal
चलो
antennas
ठीक है
is basically
पता नहीं
around a particular frequency
हाँ
you are
उन्होंने
getting
तो गाली
2-3
निकाली
different frequencies, but
हाँ
in this
हाँ
case, in the graphene
चलो
case, you can extend the number of layers by which you can get the reconfigurability around
सूट्स पर भी
two
ऑफ थी
different frequencies, around two different
सूट्स
frequencies.
तो मुझे मैम
So from
पसंद नहीं
this
आते
reflection
देखने से ना
coefficient
ऑनलाइन सच
plot, you can
बताऊं
mark
मतलब समझ नहीं लगता वो कैसे
two
लगेंगे कि
bunch
नहीं
of
वहाँ
reconfigurable
क्या ना
frequencies, right? And that
हाँ
that has been achieved by applying the Fermi energy in this particular frequency, in this particular range, 0.8 to 1.2 electron volts.
मुझे आपके साथ ही रहना चाहिए था
And
शॉपिंग
in
से
this
पहले
case also,
पता
in
है
two
कितने की
layer case
शॉपिंग कर
also,
चुके हैं मेरे
we
ख्याल
found that
60-65
it
की
is
शॉपिंग हो
maintaining
चुकी
that
है
input
कपड़ों की
impedance.
सिर्फ एक्स्ट्रा स्पैन के नहीं और अभी हाँ
The reconfigurable frequency reconfigurable antenna is maintaining that frequency, the input impedance.
हाँ ना मैं तो मैम सिंपल मेरा मैक्सिमम जो सबसे हाईएस्ट है वो 4300 का एक सूट है इससे नीचे
So it is maintaining that input impedance. The meaning you need not to bother about the feeding. Right?
ना
Then we tested its reduction
लिए
pattern.
भी कोई की पसंद ही करके रखे हैं
So the single layer
जल्दी
graphene flexible antenna concept can be extended to bi-layer graphene antenna concept, right? You can find the details of this analysis in these publications.
मेरी तो पूजा होगी आप भी कोई पूजा करा लो मेरी वो 3 दिन की पूजा होगी हवन हो गया और फेरे भी हो गया अग्निदेव से शादी
how much more time I'm having?
कल ही खत्म हुआ है
Sir, we can continue up to 1:30, including question answer
मतलब
session.
अग्नि के
So we
सामने
can keep
बोला कि
10 to
फेरे
15
चार
minutes
ऐसे लो
for
और
question answer.
3 दिन हवन चला और तीनों ही दिन पूजा भी चली
Then what we did is
ये मैम काफी टाइम से पिछले 2-3 साल से था कि ये करवानी है
metal is most widely used for making
मेरा परसों
antennas.
बर्थडे था
So we thought of combining both these materials, graphene as well as metal, to see how it is affecting, how the presence of a metal is affecting these Terahertz antenna properties.
Thank you.
So we again you designed a simple structure. What is that one? It's a silicon layer. Above that, the graphene is covering the entire silicon layer, and above that we took a layer of copper. The copper layer size is this one, graphene size is this, and the silicon substrate size is this one. So the graphene layer is covering the entire
तो बंदा तब होता है वैसे ज्यादा जब वो मेंटली खुश हो इमोशनली खुश हो नहीं होना मैम इंटरनली बंदा सेटल रहे ना नहीं तो फिर कुछ नहीं फर्क पड़ता
you can mark the cross-sectional view of that one.
Okay.
And
चलो कोई ना मेडिटेशन करो
again we varied the voltage applied across this graphene layer.
थैंक यू हाँ जी फ्राइडे पे मिलते हैं आ जाऊंगी मैं
What we found that no doubt it is giving a frequency reconfigurable behavior, but at the same time with the applied bias, the radiation efficiency is also varying. Is it 0.5 electron volt, 0.6 electron volt, 0.7 electron volt, 0.8 electron volt. The radiation efficiency is varying. Okay. And you can mark that because of the presence of that metal layer, in the previous case, you mark that it was maintaining that particular impedance, input impedance. But because of the presence of that metallic layer, here you can mark that the impedance is also varying. If it is only graphene layer, then it is maintaining that that input impedance. But when you are using metal with graphene, then its input impedance is also varying. Okay, that is one thing we have marked. But another thing that we found that the performance of the
Hello.
metal antennas
Yes, bro.
can also be improved by using a part of antenna
थोड़े
as
से स्वीट
graphene.
लग रहे हो.
Okay, that is also possible. So by
Okay.
using graphene, the
चलो
performance of
ठीक है ना.
metal
रखूं?
antennas can be
Okay, okay, bye.
improved. But when you are using metal in combination with graphene, you need to take proper care for the input impedance, right? Another thing that we have marked that we found the radiation pattern at all the frequency reconfigurable frequencies, 0.9 terahertz, 1.16, 1.08, 1.24. Again, in metal frequency reconfigurable antennas, you will find that when you are going from one frequency to the other frequency, the cross polarization level is also changing, and that too, the cross polarization level is very high in metal frequency reconfigurable antennas. So you need to, when you are going from one frequency to other frequency in metal reconfigurable antennas, at every level you need to check what is the cross polarization level. And in some cases, you will find that the copolarization is just copolarization level is same as that of cross polarization level, right? But in these cases, in this metal plus graphene antenna case, we found that the cross polarization level is very less compared to the copolarized level. So, as I told you, the performance of metallic antennas can be improved by using graphene. This is another aspect of that one. The cross polarization levels of
Are you marking for session?
metallic antennas can be reduced to a large extent by using graphene layer at suitable places. This is the performance of that graphene loaded planar metal antenna. You can find that at different chemical potential you see at different electron volts. No doubt you are getting frequency reconfigurability. It is working at different frequencies, but at the same time, the variation in impedance is taking place. Although it is the variation is much less, but there is a variation. When you compare this to a only graphene antenna, in this case there is a variation. But only the important thing to mark is that cross polarization level is much less compared to metal reconfigurable antennas. So these are the conclusions of this particular work, that the advantages of using graphene is reduced cross polarization level. Okay. So you can find the details of that one in this publication. So what are the things we have discussed? First, we verified that we found that because of the flexibility nature of the graphene material, it is suitable for making antennas for wearable applications. Other reasons of using this material for wearable applications is it is transparent in nature, and the behavior or the conductivity of the antenna can be changed by applying a
But he's
external
doing that
bias.
several times now.
And it is giving effect. It is acting as an effective radiator at terahertz frequencies, and terahertz radiations are non-ionizing in nature. So, unlike your X-rays, the harmful effects of this terahertz radiation is very less for human body. And after finding out that out of the three materials, carbon nanotube, then copper, then graphene, we found that graphene gives a better performance. After finding out that, we tried to improve the performance of this antennas, graphene antennas. And we tested that for making, while we make graphene based terahertz frequency reconfigurable antenna, its input impedance remains the same. So I extended that to make bilayer graphene antennas, and finally we verified the performance of a metal. These are few of our publications. For the detailed analysis, you can see these publications. Thank you very much for your patience hearing. If there are any questions, I will be interested to ask that one.
Thank you very much, sir, for such an informative and interesting session. So, sir, there are few questions in the chat box. So,
Sure.
may I read these questions?
Yeah, sure.
Okay, sir, the first question which was asked during the presentation was, will SAR value increase when graphene is used as a material for shield in mobile phone applications?
Which application?
Mobile phone applications. Will SAR value increase when graphene is used as a material for shield in mobile phone application?
Okay. First thing is the mobile frequency is very less, right? So at present, it has been found that these graphene antennas are working properly at or working as effective radiators or receivers only at terahertz frequency, right? If you study the literature, you will find very less application of graphene in low frequencies, right? So all because the it has not been explored much at lower frequencies. So I can't say at present what will happen to that SAR value.
Okay. Thank you, sir. Thank you, sir. And so next question. Yes. What materials can be combined with graphene?
Graphene itself is a very transparent material. Okay.
Okay, sir.
And at the same time, this particular material can be used as conductor, as a dielectric, as an insulator. So there are papers where people have used this as a dielectric, and there are papers where people have used as a conductor. Okay, so by making while making the graphene material itself, you can make it as either a dielectric or a conductor, and in all the cases, the transparency remains almost the same. So you can't mark whether just by observing the material, you can't mark whether it is acting as a conductor or a dielectric. So the transparency remains the same.
Okay, sir. Okay, thank you. And the next query is the conventional graphene or carbon nanotubes can be directly used for antenna applications, or they are synthesized to improve the electrical properties?
Nowadays, graphene inks are available commercially, but in laboratory, people are trying to use pure graphene material. Okay, so if it is a pure graphene material, you will get better performance when you are using that as antennas. But as far as antenna applications are there, you can use commercially available. See, graphene is you can find it in powder form, or nowadays it is available in ink form, graphene ink form. So use that ink to paste it on a particular substrate, so that you can make graphene based antennas. But if you are purchasing graphene flax or graphene in powder form, then somehow you have to make it convert it to liquid form. Then only you can paste it on the substrate. Otherwise, not.
Okay, sir. Okay. Thank you, sir. Sir, again, next question is related to the properties of graphene material. The question is, what are the properties of graphene materials like permittivity, thickness, loss agent, such properties?
These particular things you can find from any standard paper or standard book on graphene. You can see our papers also. There we have mentioned the specific properties of graphene. If you see any of our publications, like this second one, performance of graphene plasmonic antenna in comparison with their counterparts, there, or the third one also, you can find all the properties of graphene. In this presentation, also in a tabular form, I showed you the graphene properties.
Yes, sir. Sir, next question is, what switching elements were used for the terahertz reconfigurable antennas?
Yeah, that's a good question. See, if it is a metal frequency reconfigurable antenna, there you need these switching elements, which complicates the structure, the antenna structure. But here, as I told you, you are not using any switching material. You are not using any extra thing for switching mechanism. How you are getting that reconfigurability? By applying a gate bias or external bias across that graphene material. So that changes the conductivity, that in turn changes the antenna properties. So compared to metal frequency reconfigurable antenna, you don't need any other extra switching material or switching element to get this frequency reconfigurability. That is the beauty of these antennas.
Thank you, sir. Thank you. So again, there is one question related to the size of the antenna. How to decide and optimize size of the terahertz antenna?
My advice is you go through our second and third paper. There we have derived a closed form formula for resonant frequency of terahertz dipole antennas. It is applicable for other terahertz antennas also. So from that you can find out what size of layer or what size of antenna you need to design for terahertz frequencies. The closed form formula is there in that paper.
Yes, sir. Thank you, sir. Sir, next question is, graphene is suitable. Is graphene suitable? I'm not understanding the question. Graphene is suitable designing electrode for accurate measure of signals from brain, something like that. Participant Shri Dilip Kumar Kushwaha, can you again write your question? So I'm not getting actually the question.
खांसी बुखार या सांस लेने में कठिनाई होने
पर meantime we can
1075 पर संपर्क करें.
Refer to this question. Please mention about fabrication of graphene based terahertz antenna.
All the results, all the derivations that I showed you that we did at present, we did it in simulation stage. We have also not designed fabricated the antenna. We tried to fabricate, but the final product was not that good. But we are at present in the process of designing that one. As far as our place is concerned, we don't have that particular facility, but we are trying to contact other people to design those antennas.
Okay, sir. Okay, thank you. Sir, next question is, any particular book or research paper as beginners in the field of graphene terahertz antenna?
Again, question.
Any particular book or research paper as beginners in the field of graphene terahertz antenna?
Yeah, all these papers are for beginners only. The papers that I am showing in this slide are for beginners only.
So participants,
you can see these papers and you see the references that has been used in these papers. There you will find the papers for the beginners.
Okay, sir. Thank you. Sir, next is the terahertz antenna can be fabricated on silicon substrate or glass substrate for direct growing CNT?
Silicon substrate. And if you see this paper number 4, there we found the title is Impact of Silicon based substrate on Graphene Terahertz antennas. So if you, because there are different types of silicon substrates, we conducted a study how it is affecting the performance of the antenna also. You can see that particular paper.
Sir, next question is I think not directly related to today's topic, but I am reading, so if you like to answer. Graphene is suitable for designing electrode for accurate measure of signals from brain. Measurement of signals from brain. Suitability of graphene for designing electrode for accurate measurement of signals from brain, including microwaves. I think related to measurement of brain signals.
I don't have much idea about that.
It's out of context theory. So next is what are the limitations in fabricating terahertz antenna? Again, related to fabrication.
As I told you, the fabrication process is not that easy. You need very sophisticated instruments to design that one. So we are also in that particular phase. Although we have fabricated one piece at our place, but we didn't get the final product a good one. So we are trying to contact other people
मोना
where
कह
they
रही
are
फोन
having
आया
this
था कि तूने ट्रॉली
fabrication
ट्रॉली
facility.
खरीद ली हुई है, वैसी बात होने लगी.
So once getting some experience on fabrication of
एक
graphene
तो ना
based
इस
antennas,
कोर्स के
I
बच्चे
can
दुखी
answer
कर दिए,
that
बैग
properly.
वगैरह.
Yes. So thank you, sir. I think, sir, if we can do
तो कहती
last question.
सेल चल रही है,
Few more
10,000 का बैग
questions.
2800
So this
रुपए
is
में मिला.
related to, sir, simulation software. Which software
कहती तू
is used
पागल
to
है, तूने
simulate
खरीद
these
क्यों लिया.
antennas? And related to this is
कहती
if
मैंने
any
250 का लिया ट्रॉली बैग,
way of
10,000 का है वो.
simulating using
वो भी
CST.
किसका, अमेरिकन टूरिस्टर का.
Yeah, all these simulations that I showed you is in
हाँ,
CST
वो
only.
सेल चल रही है ना,
Specific
बिग बिलियन डे
cases
सेल
are
है,
there
16
where
से
we
22.
have used HFSS. But the only thing you need to know that the graphene
उसने बोला है कि
properties
मेरे
are
साथ चल
not
के
there in
मेकअप
the
का सामान
library
ले
of
लिए, दुकान से मत खरीदो,
CST or
वहाँ बहुत महंगा
HFSS.
मिलेगा.
What you have to do,
तो मेरे साथ
you
चलियो
use
फ्राइडे
the
को या
formulas, find
सैटरडे
out the properties, include that in
कब मिलेगी.
the graphene CST library or
मिल
the
जाएगी, चलो
simulator library in whatever
बुखार ना
maybe
चढ़े ना बस
the
बीच में.
simulator that you are using, whether it is CST or HFSS.
ज्यादा.
So include that in the library, then simulate your structure. You can't directly simulate your structure.
So thank you, sir. Related to this is any open source simulation tools that students searchers can get access for.
I don't have that idea. I don't know. At present, no open source is
Okay, bye.
available as far as Terahertz antennas are there.
Okay. So I think, sir, with this we have discussed all the queries of the participants. So participants, if you have any quick query, then you can type in the chat box. So otherwise, I will take this opportunity to thank